question 2 walks us through how to do a chi-square test. Let's rewind for a second and talk about chi-square tests. So to rewind a step further, this week we're working with bivariate data. That refers to data with two variables. Sometimes you might call those x and y. And so oftentimes when we have bivariate data, the question we want to answer is how our two variables are related, or if they're related at all. We have a couple different tools now to analyze bivariate data. One of those tools is called a chi-square test. And a chi-squared test answers, are x and y related or associated? And chi-square tests are only appropriate when we have categorical variables. Our other tool for analyzing bivariate data is called linear regression. Linear regression answers, how are x and y linearly related? We'll revisit this in a later question on this worksheet. And we use linear regression when we're working with continuous variables. So now we know what each of these two tools are for and when it's appropriate to use them. So now let's go back to talking about a chi-square test. To do a chi-square test, let's go over the procedure. For a chi-square test. Our first step, anytime we're doing a statistical test, is to make a claim. This is the claim that we want to test whether it's true or not. And for a chi-square test, we always make the same claim. And that claim is that our two variables, let me phrase this another way. Our claim is that there is no association, no relationship between our two variables. I'm putting our two variable names in blanks. You should fill in the blank with whatever your two variables are. For example, maybe your data is about how old people are and what their age is and how much money they earn. So in that case, your claim would be there is no association between age and income, your two variables. Okay. Now, the next thing that we want to do when we do a chi-square test is we want to make sure that necessary conditions have been met, that a chi-square test is actually appropriate for our data. So we want to check whether assumptions are necessary assumptions. Are true. Whether our necessary conditions for conducting a chi-square test have been met. So let's go down here where we've listed out what exactly these conditions are. So the first condition that we have to check to verify whether it's true is whether our data is of the correct type. In other words, that our data are counts. So let's go to our example here in question 2. In question 2, our example is that we have medical researchers who have enlisted 90 people for a study. And in this study, they're dividing these 90 people into 3 groups and giving each of them a different treatment. One is getting a placebo, one is getting a natural remedy, and one is getting a prescription drug. So our one variable is treatment. And then after the end of the study, they're going to measure they're going to diagnose people and see what happened to their depression, whether their depression came back after the treatment or whether their depression went away, so to speak. So in our table, we can see that these numbers, for example, this first one, 24, this table, our data tells me that there were 30 people who got the placebo treatment, and 24 of them who got the placebo saw their depression return after the end of treatment. So each of these numbers here is a count of people in each group or category. So this condition has been met. The next condition that we want to check on is independence. So the independence assumption, all that's saying is that the counts in each cell should be independent from one another. In other words, just because this one is 24, that shouldn't somehow imply that this next one is 22. In general, with this assumption, independence, we assume it's true unless we're told otherwise, because it's a little difficult for us to verify on our own. Independence is usually a natural consequence of having random assignment into groups. Our next condition that we want to check is called randomization. And what that requires is that the people in our study, the people in our sample, need to be randomly chosen from the population. In other words, the people in our study need to be a random sample from the population. Again, with this one, we typically assume it's true unless we're told otherwise. Our last condition says that a certain quantity called the expected cell count or expected cell frequency needs to be at least 5 for each cell in the table. Let's come back to that in a second. We'll come back to checking this assumption because first we need to talk about what the expected cell count is and how we find it. So that brings us to the third step of a chi-square test. Here we need to calculate the expected cell count, or the expected count, for each cell. And I'm going to write down a formula here. Our formula for calculating the expected cell counts is we take the row total times the column total divided by the grand total. So I'll bring this down here. Let's go ahead and calculate all the expected cell counts. So I'm going to introduce some terminology here. In this table, our data that we've been given, these numbers here, these counts, we call these the observed counts. And you'll notice that in this table, they've left us some blank spaces and parentheses. This is where we're going to fill in the expected counts. So let's go ahead and do that using our formula here. So we're going to go ahead and calculate the expected counts for each cell. So first, let's do 24. So our formula says that we take the row total, so the total in the row that 24 is in, which is this first row. The total here, we've seen 24 plus 22 plus 14 is 60. The column total is 24 plus 6, which is 30. The grand total is the total number of counts in our entire table. So 24 plus 22 plus 14 plus 16 plus 8 plus 6 is 90. So our expected cell count for this first cell is 60 times 30 times 90, which is 20. We'll do the same for each cell. We'll do it for 22 now. The row total here is 60. Column total here is 30. Grand total is still 90. 60 times 30 divided by 90 again is 20. And same here. You'll notice that in this first row, the expected cell counts are the same for every entry in this row. This is a special case. It's not always like this. The reason all of these cell expected counts are the same is because we have the same column totals in every column. There's 30 people in each treatment group. That won't always be the case. Oftentimes we'll deal with scenarios where the column totals may be different. And in that case, the expected counts will vary in each row. Okay, so now let's go to the second row. Here, now the expected count will be the row total, 6 plus 8 plus 16, which is 30. The column total is still 30. And the grand total is still 90. So our expected count, if I plug this into my calculator, I'll get 10. And if I calculate the rest of these expected counts in this row, I will again get 10 for each. Okay, so now we've calculated the expected counts. So let's circle back to this last assumption that we needed to check. This last assumption requires that the expected cell count in each cell is at least 5. Well, I can see that 20 is certainly greater than 5, 10 is certainly greater than 5, so every cell is okay. So this assumption we can now check off as having been met. Okay, so now we're getting to the last few steps of the chi-squared test. We've done all the setup. Now we can calculate the test statistic. And this is the number that we're going to use to help us make our conclusion, to determine whether this claim is true or not. And our test statistic for a chi-squared test is called the chi-squared value. This curly x is the Greek letter chi. And our formula for calculating the chi-squared value is, for each cell, you take the observed count, I'll write an O, subtract the expected count, square it, and divide by the expected count. Do that for each cell, and add up each of those values. That's this big Greek letter, sigma here, tells us that we should calculate this quantity for each cell and then add all of those up. So let's go ahead and do that. So we have our formula right here. Let me bring our table down to help us calculate it. All right. So for each cell, we're going to take the observed minus the expected, square it, and divide by the expected. So let's go cell by cell. So for the first one, we'll take 24, subtract 20, square it, and divide by 20. Then for the second cell, 22 minus 20 over 20, squared in the numerator. And then I'll fill in for the rest of the cells. 14 minus 20 squared over 20, 6 minus 10 squared over 10, 8 minus 10 squared over 10, and last 16 minus 10 squared over 10. I've just gone cell by cell. The order in which you go through the cells is not important, so long as you reach all of them. Okay, so now I'll just simplify these a bit. 24 minus 20 is 4. 4 squared is 16 divided by 20. 22 minus 20 squared is 2. 2 squared is 4 over 20. This would be 36 over 20. 16 over 20. Nope, 16 over 10. 4 over 10. And 36 over 10. So then if I plug this into my calculator, let me see what I get. I should get, for my final chi-squared value, I should get 8.4. Okay, so now the question is, I've calculated my test statistic, found my chi-squared value. How do I use this number to make a decision about whether a claim is true or not? And the answer to that is we use our chi-squared value to find a specific probability. That probability is called the p-value. So I'll write that up here. So we need to calculate the test statistic. And once we've done that, we use the test statistic, we use the chi-squared value to find the p-value. The p-value is the probability of seeing a test statistic value as or more extreme, in other words, greater than or equal to, then, and I'll put this in parentheses, the chi-squared value calculated in step 4 under the assumption, assuming that the claim that we originally made is true. So I'll say that again. The p-value is the probability, assuming that our claim is true, assuming that there is no relationship between our two variables. It's the probability of seeing a chi-squared value as or more extreme than, in our case, 8.4. How do we find this p-value? Well, the good news is that calculating it by hand is out of the scope of our class. It involves some calculus. So instead, we use our computer program called Minitab to find the p-value based on our chi-squared test statistic. And so here, and just like on any other written assignment, we'll give you the p-value if you don't have access to Minitab. So Minitab has told us that for chi-squared value of 8.4, the associated p-value is 0.015. So we found our p-value, and this is what we will use to make our conclusion. We've reached the last step. So make a conclusion. If the p-value is really small, in statistics, a really small probability, in our case, is anything less than 0.05. This is our common threshold that we use in statistics. If our p-value is really small, then we should reject our claim. In other words, we should conclude that there is a relationship between our two variables. And so conversely, if the p-value is not small, if it's greater than or equal to 0.05, we should fail to reject our original claim and conclude that there is no relationship after all. So I just want to take a moment and talk about what does it mean for a p-value to be really, or why do we reject our claim if the p-value is really small? So going back to our definition of what a p-value is the probability of seeing a chi-squared value greater than or equal to the one we calculated from the data, assuming that the claim were true, assuming that there were no relationship between x and y. So if this probability is really small, that means that it's really unlikely that we'd see a chi-squared value like the one we did if the claim were true. So therefore, when that probability is really small, when it's really unlikely, that's why we reject our claim. Because the chances are so minuscule that this would happen if the claim were true, we have no choice but to conclude that actually our claim is false. It's not true after all. So that's why we reject our claim when the p-value is less than 0.05. So let's go back to our example. We said, or Minitab found for us, that based on our chi-squared value, this p-value is really small. Our p-value is 0.015, which is definitely less than 0.05, right? 1.5% is definitely less than 5%. Therefore, what should our conclusion be? Our p-value is really small. Therefore, we should reject our claim and conclude that there is a relationship between our two variables, the treatment that patients received for their depression and their diagnosis at the end of treatment. And that is our chi-square test.